In this session, I am going to explain about filters, concept of filters. In these filters, the concepts that I am going to explain here are: first one is introduction, second one is characteristic of filters, third one is constant K low pass filter, fourth one is constant K high pass filter, fifth one is band pass filter, and last sixth one band stop filter. The other name for this band stop filter is also called as notch filter or band elimination filter. Band elimination filter. Okay. So these are the 6 concepts that I am going to explain in this session. So first one, in this introduction will have the different concepts. That is, first one is the definitions and definitions of filters and classifications of filters. This is the first one. Second one is T and pi type of networks, for filters. Next, third one is characteristic impedance, it is represented with the letter of Z0. Fourth one is propagation constant, which is represented with the letter of gamma. Okay, so to analyze these concepts, these basics are required to analyze the remaining concepts of filters. So first let me start with these definitions. So what is meant by filter? What are the different types of filters? Let me explain here. So filter, first one, filter definition. So we can define it as, it is a frequency selective network which will possess certain range or certain band of frequencies, nothing but pass band, and attenuates or stops other band of frequencies or other range of frequencies, nothing but stop band. Okay, let me write here. It is a frequency selective network, which will possess the signals having certain range or band of frequencies. So this certain band is nothing but pass band, and attenuates the signals having certain range or certain band of frequencies. This is nothing but stop band. Attenuation means reducing the strength of the signal. Amplification means increasing the strength of the signal. Here attenuation means reducing the strength of the signal, means we are eliminating that signals. Okay, so it is a frequency selective network which will process the signals having certain range of frequencies. That range is nothing but pass band, and attenuates the signals having certain range of frequencies or certain range or band of frequencies, nothing but stop band. And the frequency, next thing here is the frequency which separates the pass band and stop band is nothing but is known as cutoff frequency. It is cutoff frequency. Normally it is represented with FC, cutoff frequency. And another point here is these filters are normally constructed with reactive elements, purely reactive elements. The filters are constructed with purely reactive elements. Okay, this is about the information or definition of a filter. Next, this classification of filters. These filters are classified on the basis of frequency. Depending upon the frequency, these filters are classified as the filters are classified based on the frequency. Or first one, low pass filter. Second one, high pass filter. Third one, band pass filter. And fourth one, band stop filter. So these are the 4 filters that we are going to study in this filters concept. Filter is nothing but it is the definition for filters. These are the classification of the filters: low pass, high pass, band pass and band stop filters. So first let me explain the definition, or let me explain about the low pass filter. low pass filter. So it is a filter which will allows the low frequency signals. Simply we can define like this, or it is a filter which will allows the signals from the signals with the frequencies ranges from 0 to certain frequency, and that certain frequency is nothing but the cutoff frequency. So let me draw this. It is, let us assume it is the frequency versus the amplitude or the strength of the signal. So I can draw the waveform between the frequency versus this amplitude or the strength of the signal like this. So this is the cutoff frequency. It is the frequency 0 to we are varying this frequency. So this is the cutoff frequency, and this low pass filter allows the signals having the frequency from 0 to certain range of frequency, certain frequency, nothing but the cutoff frequency. That means it is the pass band and attenuates the signals having the frequency above this cutoff frequency. So this is nothing but stop band. So I can call it as pass band. It is pass band, and this one is stop band. It is stop band. So it allows only the low frequency signals, this low pass filter. So I can define this low pass filter as it is a filter. It is a filter which will allow the signals having the frequency range from 0 to certain frequency, known as cutoff frequency. Certain frequency is cutoff frequency. Certain frequency having the frequency range from 0 to certain frequency, known as cutoff frequency. Okay. And attenuates or stops the signals having the frequencies above cutoff frequency. So this filter allows this range of frequency only, so that this band is nothing but, or this range of frequency is nothing but pass band. It is nothing but stop band, and the frequency which will separates this pass band and stop band is nothing but cutoff frequency. So this is about the low pass filter. Next thing is high pass filter. High pass filter. So it is opposite that of this low pass filter. Let me draw the graph between the amplitude versus frequency. So this is the strength or amplitude of the signal. It is the cutoff frequency Fc. This high pass filter is the filter which will allows the high frequency signals, or we can define it as it is a filter which will allow the signals having the frequency range from cutoff frequency Fc to infinity, and attenuates the signals having the frequencies from 0 to cutoff frequency. That means it will allows, this is here, it is pass band, it is pass band, and this is stop band. This is stop band. Okay. So this allows these frequencies and attenuates these frequency signals. Okay, let me define here. It is a filter which will allow the signals, which will allow the signals having the frequency range from cutoff frequency to infinity, think about infinity, and attenuates the signals having the frequencies ranges from 0 to cutoff frequency Fc. Okay, so this is about the definition of this high pass filter. Next, let me define this band pass filter now. Next thing here is band pass filter. Right. So here let me draw this diagram which will represents the band pass filter. So this is a graph between this amplitude of the signal versus the frequency of the signal. So I can draw this one as like this one. So here it is lower cutoff frequency F1 or Fc1. F1, let us consider it as F1, and it is considered as F2. Okay, and here this band pass filter allows this band of frequencies only. That means between this allows the signals which is having the range from F1 to F2, and attenuates the signals above this cutoff frequency known as upper cutoff frequency, and attenuates the signals having the frequency below the lower cutoff frequency. It is nothing but lower cutoff frequency, it is nothing but upper cutoff frequency. So this one is nothing but pass band, and this is stop band, this is also stop band. Right. So let me define it. And also this frequency is nothing but lower cutoff frequency, and this one is nothing but upper cutoff frequency. Right. So this band pass filter, so this can be defined as it is a filter which will allows the signals having the frequency having these frequencies within certain range, within certain range or band. So it allows within this certain range of frequencies. Certain range or band, and attenuates above, attenuates the signals having the frequencies above and below cutoff frequencies. So we can define like this. So this is the definition of band pass filter. Next thing here is band stop filter. Band stop filter. So it is completely opposite to that of this band pass filter. Let me draw the this graph between the amplitude of the strength of the amplitude of the signal, or strength or amplitude of the signal versus the frequency f. So this is the amplitude or strength of the signal. So it is band stop filter. So within this band, it stops the signals or attenuates the signals. Above and below this cutoff frequency, it is able to allow the signals. The same thing I am going to write here, draw here. So this is the lower cutoff frequency f1, and it is upper cutoff frequency f2. This one. So this is a band stop filter. It stops this band and allows this frequency of the signals below the lower cutoff frequency and above the upper cutoff frequencies signals. This band stop filter allows, and for this range of signals or for this band of the signals, it stops the signals or attenuates the signals. That is the reason why it is called as band stop filter. So it is band stop or stop band. It is nothing but stop band, and this is nothing but pass band. This is also pass band. Okay, so we can define it as it is a filter. It is a filter which will allow the signals having the frequencies above and below cutoff frequencies and attenuates or attenuates the signals within certain band Nothing but this band is f2 minus f1. We can also call it as f2 minus f1 or stop band. So we can define these filters like this. What is meant by filter? Classification of the filters: low pass filter, low pass filter, high pass filter, band pass and band stop filters definitions. Next, so the next concept here is, let me, T and pi type of networks. T and pi type networks. T and pi type networks of filters. So this is the concept. These filters normally constructed with these type of configurations, that is T and pi type of network. So first let me draw the T network. So it is in the form of T, as we already know that. So this is the form of T. Right. Here pi network. Let me draw the pi network also. Okay, here this T network, it is nothing but the T network, and this is pi network. These filters are constructed with this help of these configurations, T and pi type of configurations. Here I can represent it as Z1 by 2. It is also Z1 by 2. It is Z2. This is nothing but series branch, and these are nothing but shunt branches, series branches. And here, if you consider this pi network, this is represented as 2Z2. Instead of Z2, it is 2Z2. Here it is Z1, and this is 2Z2. It is the representation of these T and pi type of networks in case of filters. Okay, next, coming to this next concept here is characteristic impedances. So okay, here it is 1 dash. It is like a 2-port network, 2 dash, 1 dash. It is 2 dash. Next concept here is characteristic impedance. Characteristic impedance. Normally it is represented with a letter of Z0. Okay. So how to define this characteristic impedance? Now let me explain. It is a transmission line having phase and neutral like that. It is a transmission line, and we will give the supply for this transmission line the form of voltage. Whenever we apply the supply in the form of voltage for this transmission line, this current will circulate in this transmission line, or the current will flow in this transmission line. If you consider this transmission line having the length of infinity, then the input impedance of this transmission line is nothing but the characteristic impedance. Finally, we can define this characteristic impedance as it is the input impedance of the infinite length transmission line. So let me define it. the input impedance, the input impedance, the input impedance of infinite transmission line is known as characteristic impedance. Okay, and it is represented with Z0 anyway, we know that. And coming to this characteristic impedance for T type of networks and pi type of network, I will find this characteristic impedance. So the characteristic impedance for T type of network, let me draw the T type of network here. This is a T type of network. For this T type of network, T type of network is nothing but this is the transmission line can be represented either in the form of T type or in the form of pi type. So first let me explain the characteristic impedance for a T type network. So we know that it is Z1 by 2, it is Z1 by 2, and it is Z1 by 2, it is Z2. What is this Z1 and Z2? We know that these are the impedances. Okay. Next, if you apply supply, current will flow like this. Okay. And the ratio of the input impedance of an infinite transmission line is nothing but characteristic impedance. So let us consider this input impedance is Z in here, and this line or this transmission line, we can make this transmission line as an infinite length transmission line by connecting this, by terminating this transmission line with the impedance having this characteristic impedance. That means this input impedance, okay, the input impedance of a infinite transmission line is nothing but the characteristic impedance. I can make this transmission line with infinite length by connecting or by terminating this transmission line with this characteristic impedance. So now it is called as infinite length transmission line. Now what is the input impedance of a transmission line which is having the length of the infinite length? Nothing but it is characteristic impedance. So it is Z0. It is Z0, it is also Z0. Now for this if I find the equivalent impedance or input impedance of this transmission line, these two are connected in series. For this series connection, it is in parallel. For this parallel combination of these elements, it is connected in series. Now I can write this input impedance Z in is equal to this Z1 by 2 plus the parallel combination of this Z2 is in parallel with this series combination, that is Z1 by 2 plus Z0. So this is input impedance of this transmission line, and we know that this input impedance is nothing but it is a characteristic impedance because it is a infinite length transmission line. Now if you calculate and find this Z0 using this expression, I will get it as Z0 is equal to square root of Z1 square divided by 4 plus Z1 Z2. This expression is very important for analyzing these filters. So since it is for a T type of network, I can represent this one as Z0 T. Z0 T is equal to, it is square root of Z1 square divided by 4 plus Z1 Z2. So this is important expression, right? So it is for a T type of network. For T type of network. Next, so for T type of networks, this characteristic impedance is equal to square root of Z1 squared by 4 plus Z1 Z2. Next thing here, for T type of network, the characteristic impedance, I just found it, it is Z0 is equal to this one. Next, for pi type of network, coming to the pi type of network. For pi type network, what is the characteristic impedance? So let me draw the pi type of network here. So this is the transmission line which is represented with the help of a pi type of network, and this, if it is terminated with this Z0, if it is terminated with Z0, this line is said to be infinite length transmission line. It is 2Z2, it is also 2Z2, it is Z1, and this is 1 dash 2 dash. This is an input impedance Z in, and if it is terminated, this pi type is terminated with the characteristic impedance Z0. This line is said to be infinite length transmission line. Then the input impedance is equal to, it is characteristic impedance, that is Z0. So the input impedance of an infinite length transmission line is nothing but the characteristic impedance. This line can be called as an infinite length transmission line if it is terminated with Z0. Now if you write the expression for this Z0 input input impedance Z in is equal to, these two are connected in parallel. For this parallel combination, it is in series. So for this combination, it is in parallel. So if you find this Z in here, it is 2Z2 is in parallel with Z0 plus this Z1. For this combination, it is in parallel, that is 2 into Z2. If you find this Zin is equal to, we know that it is Z0, and if you find this expression, then we will get it as Z1 Z2 by square root of Z1 square by 4 plus Z1 Z2. And since it is pi type of network, I can write it as Z0 pi, that is equal to Z1 Z2 by, this expression is nothing but, just now we calculated that expression is Z0 T. This one is Z0 T, Z1 square by 4 plus Z1 Z2 is nothing but Z0 T. So this is Z0 T. So this is also an important expression for analyzing the filters. So keep it in a box. Right. Next, so we found the characteristic impedances for the T type of network and also for the pi type of network here. Next thing here is propagation constant. Next thing, propagation constant. Propagation constant. Normally it is represented with gamma. Okay. So for T type of network, Before that, the propagation constant, this can be represented with gamma is equal to alpha plus j beta, where alpha is the attenuation constant. Attenuation constant. This beta is nothing but phase constant. This attenuation constant will explain this signal strength whenever it is traveling from transmitter to receiver. There is a reduction, there may be chances of reducing the strength of the signal. This alpha represents that attenuation, reduction of the strength in the form of attenuation, and there is a phase shift between the input to output, or between the transmitter to receiver. There is a phase shift of the signal, okay, while the wave is propagating through the transmission line. So this can be represented with gamma is equal to alpha plus j beta. Now, for a T type of network, T type of network, you can see this. Let me draw this T type of network here. This is this is a T type of network. Okay, here for the if I want to make it as an infinite length transmission line, it has to be terminated with Z0. We already know that concept, that is Z0. It is Z0, and this is input impedance is it is okay for T type of transmission line. It is Z1 by 2. This is Z1 by 2, and it is Z2. It is 1 dash, it is 2 dash. It is an input impedance. Sorry, what I need to find here, I need to find this propagation constant. So what is meant by propagation constant? How to find this propagation constant? Let me for that what I need to do here is, I am assuming that this is the current circulating in this loop is I1, and this is the current circulating in this loop is I2, and this propagation constant is normal. It is defined mathematically. It is gamma is equal to log I1 by I2 base E. So this propagation constant, mathematically we can represent it like this. So if you write this loop equations, okay, here let me consider it is this voltage here is Vs. The voltage from here to here is Vs. Okay, so if you write the mesh equations for it, it is Vs minus I1 into this Z1 by 2 plus Z2 minus I2 into Z2 is equal to 0. And if you write the loop equation for it, then it will become, it is I2 into Z1 by 2 plus Z0 plus Z2 minus I1 into Z2 is equal to 0. So if you solve these two equations, final result that we are going to get here is, this is the final result, which is important. Sin H gamma by 2 is equal to square root of Z1 by 4Z2. So whatever the expressions that I kept it in boxes, they are important results. They are useful for analyzing the filters. We are going to use these expressions for further explanation of the filters. right? This z naught t is equal to this one, z naught pi this one, this expression along with this expression. So that is about this propagation constant of t network. And for pi network also, for pi network, for pi type of network, this propagation constant is same, that is sin h gamma by 2 is equal to square root of z1 by 4 z2. This is the propagation constant we can define mathematically. Finally, what we can say here is, for t type of, that may be a t type of network or pi type of network, this propagation constant is same. But in case of characteristic impedance, this t type, for t type of network, the characteristic impedance is z naught t. For pi type of network, the characteristic equation here is, the characteristic impedance is z naught pi is equal to z1 z2 by z naught t, or z1 z2 by square root of z1 square plus 4, z1 square by 4 plus z1 z2. But here it is square root of z1 square by 4 plus z1 z2, right? Next, so in this basics, the basics of this one, our introduction concept, definitions and classification of filters is over. T and pi type of networks for filters is over. Characteristic impedance z0 is completed. Propagation constant is also, just now I completed this concept. Next thing here is, that means introduction concept is over. Next thing, characteristic of filters. Let me explain this characteristic of filters. That is fourth one. Sorry, second concept is characteristic of filters. Characteristic of filters. I think it is fourth. Okay. Fourth page, third page, fourth page. So in this characteristic of filters, what we are going to study in this characteristic of filters is the expressions for attenuation constant alpha and phase constant beta. I am going to find the expressions for alpha and beta in this characteristic of filters, because they are important. These alpha and beta are important while the wave is propagating through the space or through the transmission line. That means how will be the signal strength is changing, and how will be the change in the phase of a signal from transmitter to receiver. Next, so in this characteristic of filters, there are two cases are there. In that case one, first case here is, if Z1 and Z2 both are same type of reactances, both are same type of reactances, then Z1 by 4 Z2. What is this Z1 by 4 Z2? Whether it is a real number or it is an imaginary number, we can find here. I can say here, for this case, if both are same type of reactances, it is a real, it is a real, sorry, it is a positive quantity. It is positive or greater than 0. We can say this, it is a positive. Sorry, here if Z1 and Z2 both are same type of reactances, then the ratio between Z1 to 4 Z2 is positive or greater than 0. For example, if Z1 is J omega L or JXL, JXL means it is JXL, I can write as J omega L. I already told you, these filters are made up of with purely reactive elements. Here if Z1 is JXL, it may be jxl or it may be minus jxc also. So if I consider jxl here, both are same type of reactances. So xl1, let us assume it is xl1 j omega l1, and for z2 it is jxl2, both are same type of reactances, then it is j omega l2. Frequency is same, these inductances are different. Now z1 by 4 z2, it is j omega l1 divided by 4 into j omega l2. This j omega will get cancelled here. It is finally l1 by 4 l2. We know that these inductances are positive, so it is positive only, that is greater than 0. Finally, what I want to say here is this z1 by 4 z2 value is positive or greater than 0. Now what is square root of z1 by 4 z2? There is no negative value here. If there is a negative value, then I can write it as it is an imaginary quantity. But here it is a positive value, so I can write it as it is a real quantity. Real quantity. There is no imaginary term here. Now, just now I wrote the expression, that is sin h gamma by 2 is equal to square root of z1 by 4 z2. Just now I wrote it out here. What is that? Sorry, here itself. That may be a T type of network, pi type of network. The result here is sin h gamma by 2 is equal to square root of z1 by 4 z2. So now this sin h gamma by 2, I can expand this expression. You know that sin h gamma by 2 is equal to sin h into gamma is nothing but alpha plus j beta by 2. So if I use the formula sin h theta is equal to sin h theta, sorry, here it is I can write as sin h alpha by 2 cos beta by 2. If I expand this expression, it will be like this, plus j into cos h alpha by 2 sin beta by 2. So this is how we can expand this expression. Now this is equal to this one, so that is sin h gamma sin h alpha by 2 cos beta by 2 plus j cos h alpha by 2 sin beta by 2, that is equal to square root of z1 by 4 z2. Just now we concluded that this square root of z1 by 4 z2 is a real quantity. That means it is not an imaginary quantity, because this z1 by 4 z2 is greater than 0. So I can write it as plus j into 0. Is it okay? That means the imaginary term here in this is 0. Only the real term is present here. That means this is the real term. It is the imaginary term. If you compare these two expressions here by comparing sin h gamma by 2 sin h alpha by 2 cos beta by 2 is equal to square root of z1 by 4 z2. This is one expression. Cos h alpha by 2 sin beta by 2 is equal to 0. It is another expression. Let me consider here this one. From this, that is let us consider this equation number 1, it is equation number 2. From equation number 2, cos h alpha by 2, it will not become, cos h alpha by 2 will not be 0. As mathematical expressions, from the mathematical expressions, this cos h theta is not at all equal to 0. Only this will become 0, that is sin beta by 2 is equal to 0. But cos h alpha by 2 is not possible to get the value 0 as per the mathematical expressions. So sin beta by 2 is equal to 0. So sin beta by 2 is equal to 0 means what is cos beta by 2 and what is the beta here? Cos beta by 2 is equal to 1, we know that, because sin square theta plus cos square theta is equal to 1. If sin theta is equal to 0, cos theta is equal to 1 here, that is okay. So cos beta by 2 is equal to 1. Then here beta I can write as beta is equal to pi or 2 pi, 3 pi, like that. Beta is equal to, normally it is represented as pi. Now it is sin h gamma. Now from expression 1, from equation or expression number 1, what is this? Cos beta by 2 is equal to anyway 1 here. Sin h alpha by 2. Sin h alpha by 2 is equal to square root of z1 by 4z2. Now alpha by 2 is equal to sin h inverse of square root of z1 by 4z2. Alpha is equal to 2 sin h inverse square root of z1 by 4z2. That means it is having this attenuation constant expression as alpha is equal to 2 sin h inverse of square root of z1 by 4z2. In this case number 1, we will get only the expression for this attenuation. That means the signal strength will be reduced, which is not desirable for us. So for certain range of frequencies, we need to reduce the strength of the signals. That is okay. That is a band stop or stop band. For other range of frequencies, this that means this alpha, this attenuation constant should be 0. That means we should not reduce the strength of the signal. But here in this case number 1, if z1 and z2 both are same type of reactances, only we will get the attenuation only. There will not be any chance of this no attenuation. So that we will not use these type of cases for the filters. So next thing here is case number 2. For case number 2. So in this case number 2, if z1 and z2 are opposite type of reactances, then now let me calculate. If z1 is equal to, suppose z1 is equal to jxl and z2 is equal to minus jxe, because both are in opposite. If it is an inductor, it should be capacitor. If it is a capacitor, it should be inductor. Now it is j omega l and it is minus j by omega c. X is equal to 1 by omega c. And if you calculate this z1 by 4 z2, it is j omega l and it is minus j by omega c. This j and this j will get cancelled. So finally it is minus omega square lc. Omega is positive, L and C values are positive here. So definitely it is a negative value which is less than 0. So for this opposite reactances, then z1 by 4 z2 is negative, and square root of z1 by 4 z2 I can make it as, if it is negative, then I can write as square root of modulus of z1 by 4 z2. I can write like this. It is an imaginary quantity which is taken out from this square root, that is minus 1. If I taken out from this square root, it will become I. Now let us substitute this thing in this sin h gamma by 2. We know that sin h gamma by 2, we know that sin h gamma by sin h gamma by 2 is equal to square root of z1 by 4z2. Since it is a, now let me write here, let me expand this. It is sin h alpha by 2 cos beta by 2 plus j cos h alpha by 2 sin beta by 2, that is equal to, it is a negative quantity, I can write as j square root of modulus of z1 by 4z2. Okay, so this one is this one plus 0 plus j into this one. This 0 is the real quantity, it is an imaginary quantity. By comparing the real and imaginary quantities in both sides of equation, then what we got here, this one is fifth one, this fifth page, this fifth page. Next, after comparing this real and the imaginary parts on both sides of this expression or equation, so the real part here is sin h alpha by 2 cos beta by 2 is equal to 0. Let us consider it is expression number 3. Next, cos h alpha by 2 sin beta by 2 is equal to square root of modulus of z1 by 4z2. It is expression number 4. Because it is already, I assume that it is one equation, second equation, it is third and fourth equations. Right. Next, using these two expressions, we can find the expressions for alpha and beta. So this is the case which is used to design the filters. This is not the case to design the filters, because we will get only the attenuation, we will not get any pass band here, we will get only stop band. But in case of second case, we will get both pass band and stop band. That may explain here how it is, how these two bands are existing from these two expressions or equations. Next, okay, so sin h alpha by 2 cos beta by 2 is equal to 0. So from this, there are two cases again from these two expressions. If sin h alpha by 2 is equal to 0, so among these two, there should be one thing should be 0. I am assuming that this is 0 and it is not equal to 0. So that is cos beta by 2 is not equal to 0. Okay. That means here sin h alpha by 2 is equal to 0. What is alpha by 2 is equal to here? Alpha by 2 is equal to sin h inverse of 0. So the value of sin h inverse of 0 is 0. So alpha by 2 is equal to 0. Alpha is equal to 0. Means it is a pass band. It is a pass band. That means the signals can be transmitted. In this case, alpha is equal to 0. And I need to find the phase shift in this pass band. So I need to find the phase shift whenever alpha is equal to 0. I need to find the alpha whenever beta is equal to pi. I will expand here, you can understand. That is In pass band, what is the expression for beta? Okay, so cos h alpha by 2 is equal to 0. What is sin h alpha by 2? Sin h alpha by 2 is equal to 0. Cos h alpha by 2, we know that cos h square theta minus sin h square theta is equal to 1. Just now we know that this cos h theta is equal to, sin h theta is equal to 0. So cos h theta is equal to 1. That is cos h alpha by 2 is equal to 1 here. Because sin h alpha by 2 is equal to 0, cos h alpha by 2 is equal to 1. So from expression 4 or from equation 4, I can write sin beta by 2 is equal to square root of modulus of z1 by 4z2. Okay. Now from this I can find the expression for beta. Beta by 2 is equal to sin inverse of square root of z1 by 4z2. It is modulus. And beta is equal to 2 sin inverse of square root of z1 by 4z2. It is modulus. So this is an important expression for analyzing the further concepts. That means this alpha is, whenever alpha is equal to 0, this is beta. So in the pass band, beta expression is this one. So this is also in pass band. So this case is under pass band only, because alpha is equal to 0. So that this is the expression for pass band. This is the value of alpha for pass band. Next, B. Instead of I made this sin h alpha by 2 is equal to 0 in this expression. Instead of sin h alpha by 2, if cos beta by 2 is equal to 0, there may be chances of becoming this cos beta by 2 is equal to 0. I make here sin h alpha by 2 is equal to 0, cos beta by 2 is not equal to 0 in first case. Next, in case number B, if from equation 3, if cos beta by 2 is equal to 0, that is, what is sin h alpha by 2? It is not equal to 0. That means alpha is not equal to 0. That means there is an attenuation. That is, alpha is not equal to 0. Alpha is not equal to 0 means it is a stop band or attenuation band or band eliminating band. So it is stop band. Right. Next, if cos beta by 2 is equal to 0, what is sin beta by 2? Sin beta by 2 is equal to, if cos beta by 2 is equal to 0, sin beta by 2 is equal to 1. Next, from equation number 4, let us substitute this sin beta by 2 is equal to 1 in this equation number 4. So I can write that expression as, from equation number 4, cos h alpha by 2 is equal to square root of modulus of z1 by 4z2, because sin beta by 2 is equal to 1 here. So I substitute that one and I found this expression. Now here alpha by 2 is equal to cos h inverse of square root of z1 by 4z2. It is modulus. Next, alpha is equal to 2 cos h inverse square root of modulus of z1 by 4z2. So this is an important expression in the stop band. In the stop band only you will get the expression for alpha. So it is for stop band. So in the stop band we will get the expression for alpha. In the pass band we will get the expression for beta. Right. So that is about the characteristic of these filters.